Okay, let's dive right into this explainer and perform a forensic engineering autopsy on one of the most infamous structural failures in history. Now, if you're interested in how we build the world around us, you have absolutely seen the footage of this bridge shaking itself to pieces. But today, we're going way beyond the surface. We're going to dig into the actual data and historical research to uncover the true mechanics behind the disaster.
Because, this iconic footage of the Tacoma Narrows Bridge tearing itself apart, it isn't just a historical disaster. It actually represents a massive turning point that forever changed how we design large-scale infrastructure. This single failure literally forced an entire industry to completely rethink the invisible forces that act on our structures.
So, to get to the bottom of this, we're going to systematically break it down. We'll start with the fall of Galloping Gertie, debunk the famous resonance myth, explain the wing analogy, dive into damping and torsional flutter, look at the structural flaws of plate girders versus trusses, and wrap up with its aeroelasticity legacy. All right, let's kick things off with Section 1, the fall of Galloping Gertie, a suspension masterpiece. Let's picture the bridge right before disaster struck. When it opened in July of 1940, the Tacoma Narrows was an absolute marvel. It was the third longest suspension bridge in the U.S., with a massive 853-meter center span. But it was incredibly narrow and slender. In fact, it was so flexible that drivers immediately noticed this wild, roller coaster-like vertical swaying. That's actually how it earned the nickname Galloping Gertie. The sway was so extreme, cars would literally disappear vertically from sight as they drove across. But here is the truly crazy part. It wasn't a massive hurricane that brought this bridge down. No way. It only took a moderate, steady wind of about 40 miles per hour on the morning of November 7th to transform that relatively harmless bouncing into a violent, bridge-destroying twist. Which brings us to Section 2, debunking the resonance myth, and why textbooks are wrong. For decades, people have blamed this whole thing on something you probably learned in high school physics, simple resonance. But listen, if anyone tells you this collapse was caused by rhythmic wind gusts perfectly matching the bridge's natural frequency, you can tell them that theory has been completely debunked by real structural engineers. As this quote from the historical research bluntly puts it, the wind that day was steady, not gusting. The resonance explanation is, frankly, worthless when you look at the actual data. So what was the actual culprit? It was a phenomenon known as aeroelastic flutter. This is a much more complex fluid dynamics interaction, where the bridge's own movement through the air feeds energy back into its twisting. It's what we call a self-excited vibration. The bridge wasn't just passively receiving energy from the wind. Its very shape and movement were actively harvesting that energy. Moving on to Section 3, the wing analogy explained. Bridge or aircraft? To really wrap our heads around this, we have to stop looking at the Tacoma Narrows as a road and start looking at it as an airplane wing. See, the designers used solid plate girders on the sides of the bridge, rather than an open deck truss. By doing this, they inadvertently turned the entire bridge deck into a giant, static airfoil. When that 40-mile-per-hour wind hit those solid, flat sides, it created swirling pockets of air, called von Karman vortices. These vortices generated lift, pushing the bridge up and down. This is the exact same principle that allows an airplane to fly, and it's totally unlike an open truss design, which would have simply let the air bleed right through harmlessly. And those aerodynamic forces, they split the bridge into a lethal two-wave twisting motion, pitching up and down at about 14 vibrations per minute. One side went up, while the other went down. It was behaving exactly like an airplane wing undergoing flutter, basically a wing trying to tear itself right off an aircraft. Now for Section 4, damping and torsional flutter, the math behind the madness. Let's look at the math that actually doomed this structure. Every physical structure vibrates, but they usually have what's called damping. That's the ability to absorb or dissipate vibrational energy so things don't get out of control. But as you can see here, as the wind velocity increased toward that 40-mile-per-hour mark, the aerodynamic forces actually eroded the bridge's intrinsic damping until it hit zero. And once the wind passed that critical threshold, the system entered a terrifying state of anti-damping. The bridge simply lacks sufficient structural or aerodynamic damping to stop the movement. This created a massive positive feedback loop. The wind hit those solid girders, the bridge twisted, that twisting altered the airflow, creating more lift, which made it twist even more. Mathematically, the oscillations literally couldn't stop themselves. They were locked in an exponential growth cycle until the steel finally just snapped. Let's dive into Section 5, plate girder versus truss, the structural flaws. When you compare the structural data of the Tacoma Narrows to a bridge that survived, like the George Washington Bridge, the fatal lack of stiffness is instantly obvious. The data shows us that the Tacoma Bridge was just way too narrow and far too shallow to resist those intense torsional forces. Get this, its depth to span ratio was an incredibly slender 1 to 350. To put that in perspective, the engineering standards for other suspension bridges at the time recommended much deeper, stiffer trusses, often with ratios greater than 1 to 90. The Tacoma's stiffening girders were only about 8 feet deep when they really should have been closer to 30 feet deep to be safe. It wasn't a bridge, it was basically a structural ribbon. Which brings us to our final section, the aeroelasticity legacy, the human factor. So you might be wondering, how did brilliant engineers make such a massive oversight? Well, it really comes down to the human factor of the 1930s. During the Great Depression, the primary goal was saving steel and cutting costs. Engineers were laser-focused on static loads, just making sure the bridge could hold its own weight and the weight of the cars. They rigorously calculated for self-gravity, but completely underestimated the dynamic physics of aeroelasticity. The tools and knowledge of the era simply didn't fully account for wind-induced dynamic loads on long, thin structures. But from this spectacular failure came an absolute revolution in civil engineering. This disaster led directly to the modern mandates we rely on today. Bridges like the Mackinac Bridge were designed specifically with the Tacoma failure in mind, using open grids to cancel lift and deep trusses rigorously tested in wind tunnels. And here's a pro tip for you. This exact legacy is why modern high-rises and large steel structures use tuned mass dampers. Those giant swinging weights you see inside skyscrapers, they artificially introduce damping to control the exact same dynamic wind forces that brought down Galloping Gertie. Ultimately, the autopsy of the Tacoma Narrows Bridge is a masterclass in the laws of physics refusing to be ignored. It's a stark reminder that nature always tests our blind spots. So as we look to the future, building ever taller, slimmer, and more materially efficient structures, it leaves us with one incredibly vital question. What invisible dynamic forces might our newest, most ambitious structures be failing to account for today?